But anyway, yes, welcome everybody. Great to have you here this morning. Lots of familiar faces in the room. We're really excited to have you here. If you're not from the Austin area or up from Houston, where you're enjoying the cool weather up here in Austin, there's only 6 more weeks of summer here. Should end usually, it's hardly ever 100 after Halloween. But today it's only like 90, so we consider this a cold snap, so you'll probably survive it. So, but we're really excited to have this activity here at TACC. And yes, feel free to visit the machines. I see at least 5 people from the systems group sitting in here who can give tours, from Tommy and Jacob over there, and Dave and John and Ari. Like all good TACC people, they're all sitting towards the back. So, but they'll be happy to, take you into the machine room, show off, yes, the immersion cooling. Unfortunately, the very newest stuff is going into our new data center, which is up towards the Dell buildings, a little north of here, but most of you have heard about that before. So, yeah, I just wanted to take a few minutes, can answer any questions you have about TACC, but talk a little bit about sort of our history in sort of cluster management software, system management software, and then what I think some of the challenges moving forward are that I expect you all to fix before Thursday, as you finish writing out the code through OpenCHAMI, so we can run that on future machines. And when I say our philosophy, I really mean Tommy Minyards, who's sitting back there. So just one slide about TACC. I think most of you know who we are, because I recognize people from our partners at the oil companies and HP and Dell and NVIDIA and the labs who've all been here just a couple of weeks ago. And yes, it's being transcribed. I know all that. So one problem with giving a talk in Zoom is you can't disable the network, which means all the interruptions still show up on your screen. You get to see my Slack messages and all sorts of good stuff as we go on. So, but obviously, because we're here at sort of near UT's downtown, this is the research campus, where all the stuff that takes too much power to be on main campus ends up. So we're the UT Research Computing Facility. We are currently funded to be the UT system, which is UTEP and Arlington and MD Anderson Cancer Center, the 15 UT institutions around the state, a few billion in research. I've forgotten how many 100,000 employees and 600,000-700,000 students at this point. So, but we're also the NSF-funded center. We've been the largest of the NSF centers for a while. And yeah, we also have contracts with NIST and NASA and NIH and DARPA and DoD and various folks to do some other computing provision, but primarily we're an NSF-funded center, and we're the home of NSF's new leadership class computing facility. For all you DOE folks in the room, the leadership class is because they were worried that would be mad if it was called the Leadership Computing Facility, because they use that name, and there's weird things that happen in DC. So, so it's the Leadership Class Computing Facility. There are almost 200 of us at TACC. Even this year, given the ongoing apocalypse, that's always a good thing. And we run about 20,000 servers. We have north of 1 million CPU cores, more than 1,000 GPUs. Seems like more of those every day. We have 4 large production systems in there, from sort of 800 to about 8,300 nodes. So that's the sort of scale we worry about for management. Plus, we have some cloud systems and Kubernetes managed and OpenStack managed. Those aren't the big production systems, but and we have a host of different storage systems, as all of you do as well. We have a pretty broad user base. In any given year, we have about 3,000 active projects we allocate to. Somewhere on the order of 40,000 users, probably 11 or 12,000 of them are actual SSH in, run a job in a production queue people. The rest come through various web gateways and stuff like that to access boxes. We've actually had about 125,000 user accounts through at this point. So first eighth of a million down, we'll work from there. Our next big system coming up that I'm not really going to talk about, except sort of tangentially to talk about system management stuff, is Horizon. Which isn't going to fit in this data center. So hence the new one we're building with Staby data centers up in Round. It has about 5,000 CPU nodes. There'll be the NVIDIA Vera chip when that comes out next summer. The one after Grace. It has, depending on how you count nodes, it'll have 2,000 of the dual GPU Grace Blackwell boards. Those are coming in about 8 weeks. hopefully a couple weeks before SC, those will start showing up on the floor. There's about 1,000 storage servers nowadays to build out a big file system. So, order 8,000, 9,000 network endpoints, at least 4 or 5 different appliance types for install and management. But that's us. That's the gist of TACC. End of that spiel. Get on the right thing. Yep. So through the years, and some of us in this room go way back in clustering, 30 plus years. I remember, when we had 8 nodes, we just do it all by hand. And there was no notion of system management software for a long time. There was also no notion of scheduler. So that was general chaos. That seems to be what the AI people are learning now, which has been very amusing to watch, even though they burned billions of dollars on it. So, but we found shortcomings in just about everything, right? So in the really old days, sort of before most of us got to TACC, it was, all by hand. But then we've done like LSF plus rocks, and rocks was a big thing for the early 2000s until we got so sick of it, we had to change it. We've tried IBM's XCAD. We ran a couple of crays for a while and stuff that is sort of endemic to how they run machines. So all of them left us with various complaints through the years. Like most people who work in computing, when you complain about software, you just give up and write your own, and then call it a standard. Hence this meeting and many others. So, but we eventually built our own tool that was called the Linux Operating System Framework because we weren't that creative. LOSF, which eventually we started putting into OpenHPC, although admittedly we haven't really kept up and maintained the release in OpenHPC that way. I blame Carl Schultz at AMD for not keeping up on that, but it was essentially OpenHPC also has Werewolf, which for a while was only stateless nodes. We believed in stateful nodes. Werewolf actually does that now, but so it was sort of the stateful alternative to Werewolf in the OpenHPC suite way back when. And really, we just haven't had the time and energy to maintain the distribution, so it probably hasn't gone as far as it perhaps should have. But the philosophy, which hasn't really changed, although the way we would like to implement it keeps changing, with things like OpenCHAMI coming down the pipe. But one is that it should be lightweight. There should be nothing that could crash in LOSF that should take out the cluster. In terms of services, things should always just keep running on their own. Nodes should have all the software they need without having to check in with central services in order to keep running. So you pick your own scheduler. Obviously, it has to talk to the scheduler. You're probably doing something to monitor nodes, but we don't specify a particular package. And in fact, we've gone from Nagios to various things through the years. Now we monitor it. And yes, if the LSF servers crash, the cluster should just keep on running and move on. It should be vendor independent. It's increasingly challenging with all the various crazy things in firmware that the vendors have that aren't vendor independent. We try and leverage other tools that we know work and are simple. We were built on Cobbler. We're still built on Cobbler for a long time. It hasn't always followed that rule of being simple, and they sort of went down a crazy path for a while, but they seem to be coming back to their fairly simple, just do provisioning without crazy stuff roots. We were almost switching away from that at one point, but we use RPMs for package management. I believe in having a local central software repository, so we're not constantly hitting somebody else's RPM servers to do this. We do sort of, we believe that since we have a fast parallel file system and a fast interconnect, we should probably actually use that for provisioning. So we put sort of a minimal stack on the nodes through the normal sort of, do your TFTP, get your IP address, have Cobbler put a little bit on there, and then start installing RPMs via Lustre and InfiniBand, or its modern equivalent, once we get up and running. So, and importantly, which is always at least my complaint with a lot of the earlier vendor solutions, is managing the cluster doesn't stop after everything's installed, right? You have to deal with the life cycle. You have to push out updates to RPMs. You have to keep all the nodes in sync. You have to revalidate nodes when they come back to manage all our modules, et cetera. So, you have to deal with incremental updates and hardware evolution, et cetera, et cetera. And then, of course, everything needs to be scriptable. Everything needs to happen through a command line interface. We don't really oppose you having a GUI if you want one, but, if you're looking at thousands of nodes, we've yet to see a GUI that's sort of useful for that. So So we've been sort of anti-GUI, which leaves many vendors dumbfounded in discussions with us. But just at thousands of nodes, what do you do, right? You need to have scripts that can go through and find every node with this characteristic and do something to it. So all scriptable command line. That leaves us with lots of issues still, despite the fact that we've been using that since I think Ranger was the first machine we provisioned at scale with LSF. So that was 2007. So the first write of that is now 18 years old. And, we've kept patching it and making some incremental improvements to it, but we haven't really done a rewrite in 18 years on it. So it is probably time to look at new stuff. One of the many reasons we're happy you're here, but so we still have all the old challenges plus all the new ones. Should we be stateful or stateless? I think Tommy and I are strongly in the stateful category. But again, yes, if your network goes down, the node shouldn't die. That you need to have at least enough stuff to boot up and run actually on the node. But there we're seeing software stack growth. I think our current image is about 100 gigabytes that we put on the node, and that's still with a bunch of libraries on shared storage, way beyond the 100 gigabytes. If you've messed with, say, I don't know, installing the entire Intel compiler suite with its own version of Python and stuff, it's about 40 gigabytes per version. So if you want to maintain 2 or 3 versions of that without, 32 of those gigabytes you never use, but unless you prune it down pretty seriously, just the raw installs, you can get to, half a terabyte software image pretty quickly, just for your base one. And of course, we have other kinds of images to deal with now, but we still have to deal with the evolving underlying standards, things like, moving from IPMI to Redfish, which we have not yet done in the LSF stuff, but and dealing with all the different kinds of firmware you have to manage in the machine. I haven't done a new count for like the Grace Blackwell nodes, but I think in the older Dell Intel boxes we were using, even before the GPUs, we had like 7 kinds of firmware in there. We had a somewhat depressing day when Tommy and I figured out which version of Linux was running on the power supply. And found out it was totally different than all the others, and yet another thing to do configuration management on and keep track of, right, is the 8,000 other copies of the OS running on the power supplies or on the DRACs or whatever else. So we still see certain versions of management software out that then presume a certain way that you operate and certain tools that you have to use that we don't believe should be in management software. And of course, the is ongoing vendor lock-in issue. Now we have the world where AI has discovered clustering. They don't really call it clustering yet. I found that the common term is data center because they don't understand the difference between the room and the machine. So you have things to manage servers, things to manage racks, and then their next scale is data center because they haven't figured out yet that where you break the storage and the interconnect, it doesn't matter if you have one more of those, you can have them in the same data center, but they're different clusters. But that sort of seems to be the terminology that's catching on is data center level management, when really they mean cluster level management. But there's a lot of people throwing a lot of money at tools in that space at the moment. So, and some of them even have a clue. So there are others. We deal with ever more complicated hardware, not only more complicated, more expensive, right? So, as we've talked about in our group many times, when nodes were $6,000, I didn't care a whole lot about node sharing. When dual Grace Blackwell nodes are $300,000, I care an awful lot about node sharing. That you give somebody to run a 1-thread MATLAB script on your $250,000 node is a lot less waste of hardware than it was when it was a $6,000 node, and we have substantially less nodes as a result. So that. So the software is growing. I mentioned the Intel compiler. User software is actually worse. There's, RPM versus SPAC, but that's just sort of the tip of the iceberg, right? If you've dealt with any of the Python package managers and people running pip and Anaconda, the great file system killers of our time, that those things are nightmares and how you cache. We have no good solutions for that at this point. We have lots of hacks around some stuff, but we don't have any sort of systemic way of this is the right way to do Python and PyTorch sort of image management. We had clusters that had software images. Now we have clusters that have software images and deployments of VMs on top of those that have software images, and then users running containers in those that have software images. So now we have lots and lots of kinds of images and applications and users with their own, and all of the module management you do doesn't matter if then people put their own container on as a way to manage modules just once, is have one version of everything in the container that fits. We have this sort of hierarchy of software images that we have to deal with at this point. That didn't used to be a problem. And then we have a huge amount of use case diversification happening. We still have batch, still the mode that eats 99% of the cycles, although less and less percent of the jobs and users. And we have batch and bare metal, we have batch plus VMs, we have batch plus VMs plus containers, or batch plus containers with no VMs. And we have all of that with shared nodes, right? And again, you're starting to see crazy solutions at that. We talked to the Run AI folks not too long ago. And they do a great job of GPU sharing, but you give up any sort of notion of the user specifying what resources they need. They just run the job, see how full the GPU is running that, and just keep scheduling stuff over. So, you don't say I need 1, 2, or 4 GPUs. You just run the job and you let Run AI figure it out. Which isn't a mode that's going to work well for any of our users who know anything about performance tuning in scientific codes, right? But that is their notion of scheduling and sharing, is that users don't tell you what their resources are, and you just run stuff, and then you run more stuff and see if it gets worse. And if it gets too much worse, you stop running more stuff. So, and what NVIDIA bought them, right? So based on that notion. So again, perfectly useful if you're trying to fit 50 Jupyter notebooks onto 3 GPUs. Not so useful if you have somebody saying, I need this many cores to run my molecular dynamics job, right? So it's just a different world in how they do that, but they think they do cluster management, just not the way that we do. So, and now we have all these other non-batch modes, right? I mentioned Jupyter, which seems to be everywhere, right? And it's ilk, similar things, but we have increasing demands. I just ordered $1 million of RTX GPUs to basically do Jupyter hubs. We have a lot of on-demand use where you always have to have an image free, right, to run the next student who shows up and wants to run in an hour. We have persistent services, which ironically is also Jupyter. If you're running the lab hub, it needs to be 24/7, but think inference services, the whole world of Kubernetes and how it schedules and runs stuff. And then increasingly, we need to think about co-scheduling these things, right? We have people who want a Jupyter notebook to drive both an inference service that's on all the time, that's co-scheduled with a simulation that calls the inference service. So maybe some of your inference services to help them in the Jupyter notebook with their code have to be on all the time. Others are on some of the time when that particular simulation is running, but they're sitting somewhere in a Jupyter VM. And they have some simulation on maybe a bunch of CPU nodes, and then they maybe have the inference services running on a bunch of GPU nodes, and we have to co-schedule these things, across essentially job queues that we didn't have to think about before. And then we have people who want various qualities of service, various real-time constraints. For us, we have everything from overnight storm chasers, where we have to give them data to send trucks out by 5 a.m. from data that comes in at 10 p.m. the night before. We have obviously just things you manage with priority, like hurricane forecasts whenever there's a tropical system in the Gulf or in the Atlantic approaching the US. We immediately switch some of the load to that stuff. We have various and sundry, like NASA space missions, and data comes in when it comes in, and it's sort of expensive to get if you flew it out into space. If you're willing to blow it up 75% of the time, there are cheaper ways to do it. But if you wanted to reliably get to space with an expensive instrument, retaking that data can be expensive, and you need to process it in a certain window, right, where before you fill up your caches of raw data. So we have like 3 of those missions running right now. So on the various machines. So a world of not only scheduling, but just all of the modes that we need to manage the cluster for. Do we need to dynamically go between Slurm and Kubernetes on different racks and things like that, or things we need to think about, and how we're moving systems around. So really, it's a great time for us to all be here and rethinking things about cluster management and building new software stacks. And Owner's going to talk to you about Dells in just a moment. So, but the AI, let's call it a disruption, for lack of a better word, the throwing trillions of dollars at stuff that, I like to call it HPC, where no one cares if the answers are right. So you can do it in 4 bits. So it creates space to change how we do things, because this is how we've always done it is not going to be a good answer in the face of the hundreds of billions of AI investment. So, if there was something that's always annoyed you, but you've never figured out how to get your boss to change it, just blame it on AI and now you can change it. So that's a useful thing and gives us some space to think about new ways to do it. But we have new iterations of schedulers. We are going to move from Swarm to Flux. We have more complex and these very expensive nodes that we have to share because, again, you see like on Amazon now, they treat an NVL72 rack as an allocatable node, a single node at a mere $765 an hour is the current rate for that. So yeah, leaving that running underutilized for a while. Not going to want to put any kind of a bill. Works out to they won't do a long-term reservation on those, but you can get 90 days for 1.65 million on one of those racks. So it's a bargain. I figured if we could do that, we could pay for all of our racks in 9 months, and then we just keep them for the next 5 years for free. So but yes, $765 an hour. How much do you want to waste on that node? Or do you want to share it? So we have, some changes in the vendor space, but we have these massive service provider players who are driving lots of changes, right? Because if Amazon decides that's how they're going to do it on their X million servers that they have right now, that's probably going to carry a lot more weight with the vendors than anything we decide to do. So for OpenCHAMI and Omnia and TOS and all the other things that are out there, thinking about new ideas, I think it's a great time to be alive. So have a great meeting. Again, we expect the perfect tool to cover all these use cases to be done by Thursday afternoon when you all depart. So that should work well. We are happy to provide test beds, resources, people. Again, we have at least 5 of our systems people in here right now. And to participate in this, if you just need recommendations for Tex-Mex and barbecue, we're here for that too. In a few minutes, I do have to go talk to NSF in about 6 minutes, and they pay all the bills, so I need to be on time-ish for that call. But take maybe a question or two and hand it back to Alex, if there are any. All right. Well, enjoy your time here. Oh, yeah. Thanks, Jim. Yeah. We do not currently, the way the funding cycles work, that's something I need to talk to NSF about in 2 years, if they still exist. Which is a caveat on virtually everything right now, unless we're living in caves with stone knives. But no, we're going to start with Grace Blackwells, then we're going to do Vera compute nodes. And that is the extent of the construction project for the leadership facility. And then everything else after that is sort of open-ended for future procurements. So, I've been trying to get them this far since we put in a proposal in late 2017. So it gives you an idea of how fast this stuff moves for us. But so no immediate plans to update to Vera Rubin. Obviously, the next chunk of money we find to go after for systems, that would be, probably the next target. But yeah, so we have a Grace Hopper machine running now. We have 600 Grace Hoppers in there, just InfiniBand connected, not as big as yours at Los Alamos, but and we have a few hundred Grace nodes we've been using on the CPU side. So by the way, if you need ARM test beds, it's another thing we can help out with for your build and test. So that's been sort of our pre-system, but we're going to do the Grace Blackwells as the big system. And as you might imagine, for us, it's the most expensive system we've ever built. It's not the most nodes, but given the pricing nowadays, it is the most power, and that seems to go up. I know Bream is here from NVIDIA, and everybody else is, but we sort of settled on this configuration, fortunately, before ChatGPT came out, when GPU pricing was still not quite stratospheric. And many kudos to NVIDIA for sticking with the deal that we cut. But they've kept the price and the quantity, but the power went up sort of every quarterly briefing for about 3 years. So I'm up about 5 megawatts from when we spec the system without making any other config changes. So it's our most expensive and most power hungry system we've ever built, even if from how many nodes do we have to keep on the fabric? It's about the same size. So yeah, but no money for Rubens just yet. So. All right. Well, again, thanks very much. I'll be in and out. I have to go teach a class down on the main campus in a bit. So, but I'll drop by when I can. But yeah, Tommy, John, other guys are here. So, make them do stuff. So back to you, Alex. Thanks.